This is the second video in the series on virtual sensors. In this video, we'll continue to look at the virtual map sensor model, and we'll introduce some common failure modes to see the impact on the estimated map. So in the last video, the estimated and actual map were very close to each other because we didn't have any failure modes applied. The sensors were all measuring reasonable values, and so therefore our estimate was very close to the actual. So in this situation shown, the map sensor measurement system has an in-range failure, which is causing the measured map that's measured at the ECM to be much lower than the actual map, which we show by a pressure gauge in the intake manifold. This could be due to a sensor issue, or it could be the wearing harness, some problem where we have resistance in the wearing harness, or it could even be a problem with the ECM itself. So even though we'll say that the actual mass airflow of 75 pounds per minute, which we had in the previous example, that hasn't changed. The ECM instead is now going to underpredict that value of mass airflow, since the density of the air, what we're measuring in the intake manifold, is being underpredicted because of that lowered manifold air pressure that we're measuring with the faulty intake manifold pressure measurement system. We're going to underpredict that mass airflow. So because of that measurement error of the density of the air, the ECM is going to calculate the mass airflow at about 60 pounds per minute, which is about 20% less than the actual mass airflow of about 75 pounds per minute. Looking at the compressor map graphic, if we enter a mass airflow of 60 pounds per minute, and we still have a turbo speed of 88,000 RPM, we're going to get a pressure ratio of about 2.7, which is higher than the actual pressure ratio of about 2.4. This 0.3 doesn't seem like a lot, but remember that the compressor intake pressure is multiplied by this pressure ratio to get the compressor outlet pressure. Therefore, even a small error in the pressure ratio estimate is going to cause a correspondingly larger error in the calculated compressor outlet pressure. So because of the incorrect mass airflow estimate of 60 pounds per minute, which is actually 75 pounds per minute, the calculated compressor outlet pressure is 14 psi absolute, which is the pressure at the inlet of the compressor, times the 2.7 compressor pressure ratio. That gives us 37.8 psi absolute. And then, of course, if we subtract 0.6 of a psi from this for the CAC pressure drop, that's going to leave us about 37.2 psi absolute, which is an estimated map. Or if we convert that to gauge pressure, we're going to see about 22.7 psi estimate gauge for boost. So if we compare this 22.7 psi gauge estimated manifold pressure to the map sensor measured pressure of 10.5 psi gauge, we can see that something is definitely wrong. We really can't determine what the problem is until we compare the map sensor measured gauge pressure to the value displayed on the physical pressure gauge. So the 19 psi we're going to compare and see that is substantially different than the 10.5 psi that's indicated by the map sensor measurement system. You may notice that in this case, the pressure indicated by the pressure gauge is actually much closer to the estimated map than the measured map from the sensor. Note that we may have a DTC with an SPN of 102, indicating a map measurement error because of this issue. However, the mass airflow is also used in the ECM air-to-fuel ratio calculation, which we'll show in later videos, is the main component or main input to the calculated exhaust manifold temperature virtual sensor. Therefore, the ECM may have thrown a DTC for exhaust manifold temperature, such as 1180.00 instead, even though the actual exhaust manifold temperature is much lower than the estimate. This DTC will likely cause a derate, which may prevent the map system DTC from ever setting, or you may end up setting both DTCs. So looking at the compressor map one more time, if the map sensor system failure was instead causing the ECM to measure map as higher than what it actually is, the ECM would over-predict the mass airflow. So it would indicate that we have much higher density of air in the intake manifold. So this would cause the compressor ratio to be under-predicted. So we would show a compressor pressure ratio that was lower than actual, and that would result in the estimated map being much lower than the actual map. So we would have the same kind of failure. It'd be in the opposite direction though. If you note on this compressor map, one thing I should mention is the region of the compressor map outside of the what look like islands or contour lines on a topographic map. You're not supposed to operate the turbocharger in those regions. That's the reason why the speed lines don't extend beyond those contour lines. So if you do operate the turbocharger in those regions, we can definitely damage the turbocharger. So the region on the left side of this is called the surge line, and anything that operates in this region, we're in danger of causing turbo surge, which will cause a lot of problems with the turbocharger. It puts a thrust load on the bearing system, and the turbocharger will actually start to disintegrate if we operate in that region too often under load. And then the region on the right is what we call the compressor choke or the stonewall line. And so this can also cause damage to the turbocharger. So we're not supposed to operate in these regions. And so if the ECM detects that it's operating in these regions, it may take measures such as a fuel derate, or in the case of VGT, changing the VGT such that we're out of that region to protect the turbocharger. Okay, so looking at another scenario, the map sensor system is again measuring the same 10.5 psi gauge pressure, which in this case is also the same value that we show on a physical gauge that's in the intake manifold. So in this case, we know that the map sensor measurement system, the sensor, the wiring, the ECM, everything is working correctly, and we're measuring the pressure correctly. Therefore, we're going to probably measure the density of the air in the intake manifold correctly. So we're going to calculate the mass airflow as 60 pounds per minute, same as we did in the previous examples. And at that same turbo speed, if we say that it's still 88,000 RPM, we're going to calculate the same estimated compressor outlet pressure of 32.7 psi absolute, subtract the pressure drop across the charge air cooler and change it into gauge pressure, and we have an estimated manifold air pressure of 22.7 psi gauge. So in this case, the physical pressure gauge and the map sensor both agree with each other. So that indicates our problem is not with the map sensor or anything there, probably in the intake manifold. In this case, we can probably say that our mass airflow estimate is probably correct. So we've got something else that's wrong. Well, the things that could be wrong is we could be measuring turbo speed incorrectly, but that sensor measurement system is pretty robust and not so prone to failure typically. So one more of the more likely causes of this would be a boost leak. So we have the charge air cooler that has a hole in it or is leaking, or we have one of the hoses, we have a clamp that's very loose, or a hose that's split, and so we're leaking our boost pressure out. So one thing on the compressor map that the manufacturer provides for the turbocharger, it's really only accurate if the compressor output is confined to some volume. So the charge air cooler, the intake manifold, we have to have that restriction, that volume that's there. Obviously, if we remove the compressor outlet hose completely from the turbocharger, the compressor outlet pressure is only going to be slightly higher than barometric pressure. So in this case, the actual exhaust manifold temperature is going to be elevated due to the reduced air to fuel ratio. So if we may have a DTC for that and a derate. So in this case, the service tool, if the service tool has a data point for showing the estimated manifold absolute pressure, we could compare that to that measured map, and that's going to help us diagnose this exhaust manifold temperature diagnostic trouble code. So one thing I should probably mention is that many virtual sensor models are only accurate under specific engine operating conditions. Oftentimes this requires a moderate or a heavy, even a heavy engine load. So ideally, the manufacturer is going to provide you that information in their service information. They'll tell you what the operating conditions are required to set each diagnostic trouble code. But I think you as technicians know that this is often not the case. So next time we'll take a look at the exhaust manifold temperature and how that is calculated.